The block of glass shown in cross-section in the figure is surrounded by air. A ray of light enters the block at its left face with an incident angle θ1 and re-emerges into the air from the right face directed parallel to the block's base. And we are to determine the initial angle at which the light entered the glass. Because there are 2 points of refraction, we expect that this problem will require 2 applications of Snell's law, surrounded by a few geometrical calculations. Let's begin by examining an enlargement of the exit surface of the glass block. We'll begin by drawing the normal to the surface because we recognize that Snell's law always involves angles as measured with respect to the normal. Because this angle is 45 degrees, so is this angle. And since that one and this one, which we'll call θ4, add up to 90, we recognize that θ4 must also be 45 degrees. We'll then be using Snell's law to relate θ4 to θ3, the angle compared to the normal inside the glass. And we recognize that n3 times the sine of θ3 is equal to n4 times the sine of θ4. This expression has only one unknown. That unknown is θ3, and so we're able to solve it easily to give the result for θ3 of 28.12 degrees. We'll now need to use a little bit of geometry to relate the angle θ3 to the angle θ2, which is the result of the Snell's law calculation as you entered the glass. By adding a horizontal line to the original figure, we can see that the angle θ2 is not only the angle between the ray and the horizontal at the entrance point, but by alternate interior angles, θ2 is also located over here. Returning to the magnified view, we again recognize that the angle θ2 will be the angle between the horizontal line and the light ray before it exits. We also recognize one more principle, and that is the angle θ4 is a vertical angle to the one indicated in green on the left. Therefore, we understand that θ4 is simply equal to the sum of θ2 and θ3. Thus, since θ4 is 45 degrees and θ3 is 28.12 degrees, we determine that θ2 must be equal to 16.87 degrees. Once we know θ2, we're able to return to the original figure and then solve for the incident angle θ1. We do that by recognizing that n1, the air, times the sine of θ1 must be equal to n2, the glass, times the sine of θ2. The only unknown is θ1, and so we're very easily able to solve for a θ1 value of 25.81 degrees. And that completes our analysis, in which we have applied Snell's law twice and a few considerations from geometry in between.